So here E, we know that E is power over area, right? As I mentioned earlier, E is power over area. So power is E into A. Or we can write P is AE. AE. But we know that E is sigma T to the power 4. So we have another equation for the total power emitted. So here the total radiant energy, the total radiant energy per unit time by a surface area A, by a surface area A is given by the above equation. So we know that E is power over area. So if I want to find the total radiant energy, we can use this equation. Once you have noted up to this, let me know. Once you have completed. Good. So I completed. Next topic, energy distribution of a black body. Energy distribution of a black body. First, I will explain the graph. After that, let's write the note. So these axes are very important. Here we have the wavelength. In this axis we have wavelength lambda, which is measured in nanometer. And here we have intensity of radiation. Okay, so in that direction we have wait, I'll write it properly. Okay, so here we have intensity of radiation, which is measured in watt meter minus 2 per nanometer. So we know this. Now here this part is the unit of E, right? And this is per nanometer. That means energy per nanometer. Did you get the idea of the unit? So this is E lambda. That means now, for example, when we take a black body, E, if I just mention E, that means from that specific area, the total energy. But if I mean E lambda, that means now this E is composed of several radiation. We might have radiation at 500 nanometer, then we might have radiation at 510 nanometer and at 600 nanometer, and the energy of each of them will be different. The energy per unit area of each of them will be different. When I say E lambda, that means we are only talking about a specific wavelength. For example, if it is E 510, that means we are only considering the energy of this specific wavelength. Is that idea clear? So if we plot the variation of each wavelength, energy due to each wavelength for different temperatures, we get a graph just like this. So these peak values, they will have a variation like this. Okay. Keep in mind the variation when you draw. So this is temperature T1, this is temperature T2, and this is temperature T3. Now, what can you tell about the area under this curve? Using the units, using this unit, you should understand. Now let's say if I draw a line like this, that will be the energy. Let's say this is 600 nanometer. For 600 nanometer, okay, then here let's say that's 550. So this will be the energy for 550, and so on. If I'm checking all these values and add all of them together, I will get the area under the curve. Okay, I will get the area under the curve. At the same time, here I will get the total energy. Total energy per unit area, power per unit area. Is that idea clear? Saja, did you get it? Now, each and every line, single line, will represent the energy of a single wave. So this line shows the energy of 550 nanometer wave, and this will show the energy of 600 nanometer wavelength. So similarly, if you are going to take each and every wavelength and add them together, you're adding all these straight lines together, right? Finally, you end up with the area under this curve, and automatically area under this curve will give you the total energy, or the total energy per unit area, power per unit area, E. Is that clear? And look, then what can we tell about temperature T1, T2, and T3? T3 has to be greater than T2, and it is greater than T1. The reason, look, when the temperature is increasing, the area under the curve will increase, right? Or you can tell, because the area under the curve is increasing, this should be the temperature. Okay, so here, look, for each and every temperature, for temperature T1, this is the wavelength that emits the maximum uh, energy. And when the temperature increase, this is the wavelength which will emit the maximum energy. And so on. What can you tell about the wavelength? Is it increasing or decreasing? Maximum lambda. Maximum lambda is decreasing, right? Lambda maximum decreases. No. Uh, so this dotted line is the path of lambda maximum. So lambda maximum decreases when temperature increase. Look, when you're increasing the temperature, lambda maximum is decreasing. Okay, so when lambda is decreasing, what can you tell about the frequency? What will happen to the frequency? It will increase. And here we have, somewhere here only we have the visible light region. So the idea is when you heat a body, it will release radiation and it will be releasing radiation in the infrared region. And when you heat it more, when we heat it more, when we heat it more only, the lambda maximum will decrease. At certain instant, it will come into the visible region. Then only we can see. So now think about metal. When we heat metal at some small temperature itself, it starts to radiate, but we are not able to see any color. When it is very hot, when it starts to become very hot, then we can see uh, red color, orange color, or yellow color, right? So that's the reason. The maximum wavelength or the maximum emitted wavelength, energy per maximum emitted wavelength comes into the visible region. Then only it becomes visible to our eye. Okay, clear with that? Draw this graph. Once you have drawn the graph, let me know. I will scroll down. Once you draw this graph, let me know. I will scroll down. Write these points. Now look, the first point, the above graph illustrates the way in which the radiation by a black body is distributed among various wavelengths. So that is clear. A black body radiation is a continuous range of wavelength for a given temperature. So the idea is, look, here in this, for this specific temperature, let's take this temperature. It has continuous wavelength, right? It has continuous wavelength. So that is what it is mentioned in the second point. For given temperature, it has continuous wavelengths. From the graph, at each temperature, the intensity at which the radiation is emitted comes to a maximum at a particular wavelength. So for a specific wavelength, for specific temperature, there's a specific maximum wavelength. We discussed that. When temperature increase, E lambda also increases at all wavelength. That means, look, when temperature increase, EM value of every wavelength is increasing, right? From here to here, look, every wavelength has increased. Okay, that is the idea of the third note. As the temperature is increased, certain amount of visible light is also emitted by the black body. We discussed that. Lambda starts to decrease, and when it comes into the visible region, we can observe. The area under the curve relevant to each temperature represents the total radiant power through unit area of all wavelength emitted from the black body. So I also discussed that. Copy this down. This part has less theory to explain, but more to write. Even if we don't write, you will forget. Okay, and let's look at this one also. Here, I have shown a path, right, for the maximum lambda. So this maximum lambda has a specific path that is like this. Lambda inversely proportional to temperature. So lambda t is equal to a constant. Okay, so this one we call as the Wein's law, Wein's displacement law. Is that clear? Nothing special there. The path of this lambda maximum and temperature has a relationship, which is an inversely proportional relationship. So we can write it as lambda into t is equal to a constant. And this we call as the Wein's displacement law. Okay. So you can copy the next note also. Did I get that idea? I uploaded the note to the group, right? So in that note, just before quantum theory of radiation, to that you must be able to copy and understand. Okay. The meeting might end in a few minutes. Have you all copied? Okay, so I'll end the meeting. Uh, I think I have uploaded, yeah, I uploaded the note. In that note, until this, this screen is visible, right? So here, we have the Wein's displacement law. As I explained now, it's just lambda t is equal to a constant. Okay. And we have a few notes. Read them and you will understand, because I have given the idea. Then there's a few example. And after that, we have two terms, emissivity and absorbivity of surface. When you read, you will understand. And note this one also to this. Okay. I will explain this part. Okay. I will explain this part and this one also. If you copy it earlier, it will be easy for us. So we can start the next topic in the next class. Okay. I'll end the session. Assalamu alaikum.